David Smith here with another Flip Classroom video. 3 tips before we start. First, remember you can pause the video anytime to catch up with your notes. Second, you can turn on the captions below so you can watch my words go by on the screen. And lastly, you can play the video at double speed if that helps you get through it faster. Today's video is a review of chapter 14 from our textbook, which is about probability distributions. So we did a lot of stuff. It was kind of complicated. I'm hoping that for you it came together in the end. So in this video, what I'm going to do is just go over the topics, take 3 or 4 boards to do that, and then I've got 2 problems to do at the end of the video. Now remember, if you're preparing for our unit test, you want to be sure to do all of the IB practice test questions. Those are most closely aligned with what you'll see on your exam for this chapter. So let's get started. So this whole unit was on probability distributions. The first section was more general, and we introduced some notation and we talked about a few things. So this notation just means that all the probabilities for a given situation have to add up to 1. And we exploit that in a lot of different ways in this chapter. So here is the sigma. Whenever you see sigma in mathematics, you should think, oh, we're adding something up. It's the sum of. So this says the probabilities where x equals x, the big X, little x is 1. So that means like if we have, if we're rolling a die, we've got 1, 2, 3, 4, 5, 6, the probability that x equals 1 plus the probability that x equals 2, probability that x equals 3, and so on all the way up to 6. All those probabilities have to add up to 1. So always remember that. That gives you shortcuts for various problems that would otherwise take you a long time by hand. Okay, let's take a look at the second thing. When you see the E, not the sigma, but the E, in our chapter that means expected value. And so the expected value for a situation can be found, well actually first off, that expected value has a special letter that's mu. And when you think expected value, you should also think mean or average because they're the same thing. So expected value, mu or mean, is just the sum of all the probabilities. This is the sum of that actual event times its probability, and then you add that up for all 3 or 4 events, and then you would that would give you your mu or your mean. So like for a die, if you're rolling a die, you would add, and you want to calculate the expected value. Actually, let's do that example. Okay, here's that example real quick. For a 6-sided die, what's our expected value? So it's going to be the probability of getting a 1 times 1 plus the probability of getting a 2 times 2 and so on. Probability of getting 3 times 3. Remember, a 6-sided die, any one side has a 1/6 chance or probability, and then we're multiplying the probability times the value. So here are all my terms that must be added up to satisfy the sigma. And so what I did here, I like to do things algebraically just because I like the challenge. So I noticed I have a 1/6 in all of these, so I factored the 1/6 out. Then I added the remainder up. I get 1/6 times 21. Expected value is 3.5. So if you roll a die one time and you're just trying to get the total number of what appears on that die, your expected is 3.5. Now don't get hung up if your expected value isn't a value you can actually get, because that's the case. Think about the expected value for flipping a coin one time. It would be 1/2 heads. That's how many heads you would expect in one flip. You're not going to get half a head. You're going to get a head or a tail. But that's how that works. All right, so after we did probability distributions kind of in that general way, we dove into the binomial distribution, which is a special kind of probability distribution, and it allows us to use some of the stuff we learned last year when we did the binomial theorem in Pascal's triangle. Now you're not going to actually need to use Pascal's triangle in this section, but it does underlie a lot of the stuff that we do, especially evaluating one of these guys here. So let's take a look at this. What we have is the probability of a certain outcome, which would be R, is given by the number of trials by the outcome. This is the combinatorics term. So let's break away for a minute. This equals this. So we have number of trials, factorial, the outcome you want, factorial, and then n minus r, factorial. Now a side note, you can put this into your calculator, and you want to do that if you're working on a calculator portion of the exam. It's foolproof. Now you should be able to analyze these algebraically as well, because there's lots of canceling that helps you out. But if I give you a problem on a test that has big factorials that don't have everything cancel downable, if that's a word, then it will be on a calculator portion of your test. So then you take the combinatorics term and you multiply it by the probability of the event actually happening times r, and then 1 minus the probability of that event times n minus r, trials minus r. So that's that formula. You won't get a million of these because these take a while, especially if it's on a non-calculator portion of the test. Okay, I want to pause this topic list. We've got more topics on this section to remind you of a few things about the binomial distribution. First off, notation. Random variable x has a binomial distribution with n and p. And remember, n is the number of trials and p is the probability of success. Now, when I say success, that leads us to four conditions that we need to be in a binomial distribution. So let's take a look at those. They're right over here. The 4 conditions are fixed number of trials. So when we're analyzing a situation, we keep the number of trials constant. Second one, the outcome is either success or failure, yes or no, heads or tails. So if you're analyzing like a dice roll and you're interested in the number of 6s you get, then the roll is either yes, I got a 6, or no, I didn't get a 6. Finally, the probability of success is constant. So with a dice roll, it is. Probability of a 6 is 1/6 all the time, doesn't changes. Finally, the trials have to be independent. So you roll the die one time, record your result. When you roll the die a second time, it doesn't matter what happened the first time. The second time has the same probability of happening. So those are the 4 conditions you need to use the binomial distribution. All right, so let's take a look at a few more things that we've talked about in our binomial distribution section. First off, expected value, really simple. Average is what that is, and we get the average just by multiplying the number of trials times the probability of success. So that would be our expected value. The variance, which is written var x, that's sigma squared. Remember, sigma is standard deviation, and you can calculate the variance just by doing the number of trials times the probability of success times the probability of failure, which is 1 minus the probability of success. So remember, we have only 2 outcomes. They have to both add to 1. So if you know 1, you just subtract it from 1 to get the other. Okay, standard deviation is just the square root of the variance. So if you know the variance, you can take the square root of that to get the standard deviation. If you know standard deviation and you want the variance, you can just square it. So here are all these different attributes. You want to pay attention to the notation. We have EX, we have var x, and then we have probability, x equals x. The notation is important, so you might get a prompt that requires you understand the notation so you know to do the right math. Okay, our third probability distribution revolves around the normal distribution. Now this is a very specific distribution, and we have 2 versions of that. We have the normal distribution, and then we have the standard normal distribution. And that one is even more specific. It's more simplified. So let's take a look at what those are and what the curve looks like. So the normal distribution is noted by random variable x, n. Okay, so instead of a b, we have an n for normal distribution. And then different things go in the parentheses. We have mu, or mean, and we have variance here, or standard deviation squared. So this is the normal distribution, okay? The standard normal is just a little more specific. We use z for that, so standard normal with our n for normal distribution. Now the average, or mu, is 0, and the standard deviation is 1, which means also the variance is 1. So this one is much more tightly tied down. It's much more, you don't put in different values for these because it's always 0 and 1 there. Now, let's take a look at the curve for the normal distribution. So it's a bell-shaped curve, rises up to the peak. The peak is the mean, median, and mode. So remember those terms from statistics from last year. In a perfect normal distribution, these three values are always the same. Now in this chapter, we're really just concerned with the mean or with mu. We don't talk too much about the median or at all about the median and the mode. Now there's some things about this curve. It's bell-shaped and it's symmetrical. So this curve is symmetrical around the mean. So if I'm looking at this section here, and as you'll see in a minute, we calculate areas, that area is going to be the same as this section here, provided these values are the same. If we did A and B there and negative A and negative B there, then that area would be the same as that area. We just know that because the curve is symmetrical. Now we exploit that quite heavily in this chapter. Now the other thing to know is that the area under the curve gives you probability. So that's what we use this distribution for. And the calculator is a really handy tool. So there's something to know. The total area under the curve for any situation equals what? Pause the video, think about that if you don't already have it. Think about that. What is the total area under this curve going to be? It's going to be 1, because the total probability for any situation always adds up to 1. So we also will exploit that at various times when we're analyzing these problems. The last thing about the graph, I find that when I'm doing complex problems, and they don't prompt me for a graph, it's really helpful to sketch that graph because then I can visually see the pieces of the probability puzzle that I'm trying to find. All right, so we end up using the calculator to tell us the area under the curve, but you're going to be prompted to figure things out, and you're trying to find these A values at times. Sometimes you're trying to find the probability, sometimes you're trying to find the A value. So what I'd like you to do is use your curve, sketch that in, we have our mu there, and sketch, like add an A. Actually, what I'm going to do is I'm going to add the A and the negative A, okay? Now, what I want you to do is take a minute and shade the area, that is the probability, for this calculation. Where is that area going to show up on your graph? All right, so less than A means that we are less than A. Notice how that's a positive A there. So it's all this area here that's going to the left of our positive A. So whatever this area is under my curve, that totals up the probability that x, the random variable x, is going to be less than that value. So we use the calculator to calculate those values, but you have to understand it in terms of the graph. I think that's very helpful. So now, pick a different color, sketch a new graph, draw that one. What probability is that one? Okay, probability x is greater than A is just that side. Okay, so really all I did with these two terms was I figured out the probability of either being less or being more than A. Pause the video a second. What do these two things have to add up to? Quick, straightforward question. They must add up to 1 because we've got the whole area with these two conditions. Okay, so with that area going all the way that way and that area going all the way that way, we should add up to 1. So if this was a problem and you did these two calculations, both these probabilities should add up to 1. Now finally, what I'd like you to do is grab a different color and sketch in that probability. So think about your graph for a second and go ahead and sketch that in. Okay, so this one is the probability that x is between negative A and positive A. So that's just this zone here between negative A and positive A. So whatever that area is, that's going to be the probability that random variable x lies between the two values of A. Now, your calculator has specific steps for putting in all these probabilities. I'm not going to go over that here, but there are other videos that have links below that take you to the YouTube videos that teach you that. There's also click steps and video link sections on our weekly planner. Make sure that when you do our unit test, when you roll up for that you know how to use your calculator to calculate these probabilities, because there's not a manual method. It requires the calculator. Action. Also, I want to remind you of one point. Greater than, less than or equal, I can put those on there and it doesn't matter. Okay, so those things don't matter. Don't get hung up on whether you include A or not. Just remember that it could be less than or equal to, and you're fine. All right, so there's a little trick that we need to do from time to time, which is called standardizing a normal distribution. So some calculators don't allow you to do just a regular normal distribution. It has to be standardized, or it has to be a standard normal. Remember, that's when mu is 0 and sigma squared is 1. So you can standardize a regular normal distribution by using the following formula. And that's that basically this gives us our z value, and that's the random variable x, the outcome, minus the average divided by sigma, by the standard deviation. And then you can use that z value to finish your calculation. So that becomes particularly important when we're solving both for mu and sigma in the same problem. That's the only way you can solve that. I'm pretty sure everywhere else in our chapter, you don't need to do that unless you're prompted to do that. So you need to have that tool in your kit bag. All right, let's do an IB exam style question that deals with a probability distribution. Notice how I didn't say binomial and I didn't say normal. This is just a probability distribution. So first one is kind of an algebra / conceptual prompt. So I have my probability situation here. Here are my outcomes, 0, 1, 2, or 3. This could be a four-sided die, it could be a spinner, whatever we have. We got 4 outcomes, and now we have the probability of each outcome. So getting a 0 is 0.2, getting a 1 is, k plus 0.25. So we don't really know what that probability is, nor do we know this one, k minus 0.05, and then we know that the probability of the outcome labeled 3 is 0.3. So our first prompt is find k. Now there's an exploit here that allows you to set up an equation that allows you to solve for k. So I want you to pause the video, see if you can take that all the way through. All right, so the exploit that you have to remember is all these things add up to 1. So check this out. Here's my equation. 1 equals, and I just put in all these things all the way straight across. Simplify that on down. I get 0.7 equals 2k. Bring that down. Finally, I get 0.15 for k. So now I want you to write down and figure out the probabilities for the 1 outcome and the 2 outcome. Pause the video and do that. So I just added my 0.15 across. I got 0.4 for the 1 outcome and I got 0.1 for the 2 outcome. Then just to double check, because I can, I added them all up here and I do get 1.0. So that's a nice confirmation that I'm doing what I'm supposed to do. Okay, second prompt. Find the expected value of x. So this is like we're going to do this thing one time. There's a spinner with 4 outcomes and we're going to add up the number. Okay, so what is the expected outcome? So you have that. We talked about that in the review section a couple, 3 or 4 boards ago. Pause the video, flip back up in your notes, do that calculation, and come back. Do that calculation. All right, here we go. Here's our basic statement from that last board we did. The expected value of x is the sum of all the individual probabilities. So x times probability of x as we go down each of the 4 outcomes that we have. So I strung that together in this big long text. There's our first outcome, 0 times 0.2, and so on for each of the other 3. I summed them up here, or simplified them and summed them. So the expected value, if we spin this spinner or roll this weird die, is going to be 1.5. Now remember, you can't get 1.5 as an outcome, but that's okay because expected value is an average. So the average outcome will be 1.5. And what that means is that if you did this 500 times and just added all these numbers up and divided by 500, you should be around 1.5. One last question. If we do 100 trials, we spin the spinner 100 times, how many 2s should we get? So pause the video, do that calculation, come back. So if you recall, the expected number of outcomes is just the number of trials times the probability of success. So the probability of success for getting a 2 is 0.1. We did 100 trials, so we do 100 times 0.1 or 10 2s. All right, let's do a probability calculation word problem. This one's going to hit on lots of different points, so make sure you can follow it through to the end. So here's our situation. We have a forest that's got tall trees in it. The tree heights are normally distributed, so nice, that allows us to use our calculator. with a mean of 45 and a standard deviation of 9, heights in meters. So here's our prompt. Find the probability that a randomly selected tree is at least 55 meters tall. So go ahead, pause the video and see what you can come up with. Maybe just state the problem with our notation and come back. Okay, here's the overall statement of our situation. We've got a normal distribution, random variable x, our mean is 45, and our variance is 9 squared, because we know that standard deviation is 9, so the variance is 9 squared. Now here's a statement of the problem. Find the probability that random variable x is greater than 55. Now this is a straightforward calculator plug-in, so if you haven't done that already, pause the video and do that plug-in. All right, here's another one. Find the probability that 3 randomly selected trees are all 55 meters or taller. So think about that. This is number 2. Think about that for a minute. It's actually a straightforward calculation. You just have to pull out the right formula for that. So pause the video, see if you can do that. All right, this one is pretty straightforward. We just use our combinatorics term. We've got a situation where we're trying to figure out what our probability of success is for 3 trials. So we have our n over r. Our number of trials is 3. Our successes are also 3. So we want that probability, or we want that number to be our 3 as well. Our probability of success, I can put 0.133 there. We're raising that to the 3rd power because that's our r from here. And then 1 minus the probability of success to the 0 power. So this term goes to 1. This term goes to 1 because that's here. Take a look at that factorial. I've worked that out, and you're going to find out that that's just 1. So really, our probability that 3 randomly selected trees are all 55 meters or higher is really just going to be that first probability that 1 tree is that high, raised to the 3rd power, which gives us 0.00235 for the probability that 3 randomly selected trees will all be 55 meters or higher. One more tree question. 50 trees are selected at random. How many would you expect to be over 55 meters tall? Pause the video, do that calc, and come back. All right, so for this one, find the expected for x being greater than 55. This is going to be the number of trials times the probability of success. So each time we select a random tree, that's a trial, and then the probability of getting that success is 0.133. So just 50 times 0.133, which is 6.67 trees. So that would be the expected value for this problem. I forget how I start that. Does it go?
Here, I can hope the video was helpful. I can hope it.
Now that you've watched the video, write down any questions you still have so you can remember to ask them in class next time we meet. Also know that you can watch the video again if you want to deepen your understanding or patch up any gaps. Finally, give me a like and subscribe if you enjoyed it.
Yeah!